ln K is only positive when K is larger than 1. Right? That's what you learn in mathematics. So if delta G is negative, I can safely say that the K value must be larger than 1. Correct, right? If the K value is larger than 1, what is the implication based on what we have learned so far? It means that the position of equilibrium must lie very much to the right. Agree? Because how did we calculate K? K is the concentration of product at equilibrium raised to the appropriate power over concentration of reactant at equilibrium raised to the appropriate power, right? So it's concentration of product at equilibrium over concentration of reactant at equilibrium. If K is larger than 1, naturally you have more product than reactant, which means that the position of equilibrium must lie very much to the right. The reaction essentially goes completely to product. Okay? Can? Right? Why you sleep? It's now being recorded. It's on LMS forever. The reaction goes essentially completely to product. Okay? And the products are more significantly abundant as compared to the reactants, right? So at equilibrium, you're going to have more product than reactant. That's why your K value will be larger than 1. So that all makes sense. Okay, if you use this equation. Okay? Consider case 2. What if your delta G0 is positive more than 0? If you look at this, if delta G0 is positive, this is negative, this is positive, this is positive, delta ln K must be negative. When ln K is negative, K must be lower than 1, right or not? When K is less than 1, ln K will be negative. So the position of equilibrium must lie very much to the left, because when K is lower than 1, the concentration of product is going to be lower than the concentration of reactants. The reactants will be largely left unreacted, and the reactants will be significantly more abundant than product at equilibrium. Okay? Which is consistent with a K value that is less than 1. Okay? Can? And the last case, when delta G0 is approximately equals to 0, or if it's equals to 0, I hope you can see that delta G0 is 0 when K is equals to 1. Because ln 1 is equals to 0. Ln 1 is equal to 0. 0 times t times r times negative sign is also 0. So when K is equals to 1, you have an equilibrium mixture. An equilibrium mixture that largely contains significant amount of both reactants and products. Okay? You don't favor more reactants over product, nor do you favor more product over reactant. Okay? Your delta G0, just to quick recap, only provides information whether the reaction is spontaneous or not. Okay? The delta G0 is a constant at a given temperature. Okay? But your delta G changes as the composition of reaction changes before finally reaching 0 at equilibrium. So there is some slight difference between delta G0 and delta G. Okay? So I want to just quickly look at the difference between delta G0 and delta G. Okay? What is the key difference between delta G and delta G? I will use the same graph. What is delta G0 using this diagram? Delta G0 is just the Gibbs energy of reactant, Gibbs energy of product. Delta G0 is just the difference here. Okay? So delta G0 depends on the change in Gibbs energy from pure reactants to pure products. Okay? So delta G naught reflects the composition at equilibrium position. Okay, when delta G naught is greater than 0, K must be less than 1, reactants are dominant, higher concentration of reactants. Okay? But delta G is the change at a point in time in the reaction composition. Okay? So delta G is not going to be the same as delta G naught. Delta G naught is just looking at pure reactant, pure product. But delta G is at different points in the composition. Okay? Can? Right, so delta G depends on the slope. Okay? Right? Now let's look at checkpoint 7. Now checkpoint 7, we'll give you about 2 minutes to try this out. Sketch on the same axis as what you find on page 28. The variation of G with progress of the reaction when K is greater than 1 and when K is less than 1. Okay? Try to sketch out how you think the two graphs will look like. Okay. Come. Okay, let's take a look at checkpoint 7. When K is larger than 1, we have already established that when K value is larger than 1, you will favor the forward reaction more. Hence, at equilibrium, you must have a larger percentage, proportion, concentration of product over reactants, right? Which means that at equilibrium, the position of the minimum must be much closer to the product than reactant. So when K is much larger than 1, the mixture will contain significantly more product than reactant. The equilibrium position must therefore lie very much to the right, where there is more product. The minimum G here must be plotted closer to the product. Because in the original graph here, it is 50% reactant, 50% product. This original line that you see on your page 27, this line here, actually represents a K value of 1. But when K value is larger than 1, it will shift like this. Okay? So I say again, this line here is when K value is equals to 1. Okay? So the next part 2, how to sketch when K value is much lesser than 1. Sorry, this last bit, delta G must be less than 0. Okay? Alright, so you're going to favor the forward spontaneous reaction. When K value is lower than 1, what do you get? When K value is lower than 1, naturally it must be at the other side, right? Because when K is much lower than 1, the reaction mixture will largely contain more reactants than product. The equilibrium position will lie very much to the left, where basically you will have an equilibrium that is very close to reactants. So most of the reactant never react. It just stays somewhere here. Okay? Why is that the case? Because your delta G naught is more than 0, so there's not much forward reaction taking place. Your reactant will still stay as reactant predominantly, right? Because the delta G naught is greater than 0. Okay? Alright? Okay? Alright, so it is still consistent with what we learned in energetics part 1 and energetics part 2, which is when we say that delta G naught is greater than 0. It means that the forward reaction is not spontaneous, so you will have reactants. But for reversible reactions, you will also have predominantly reactants as well. That's consistent. Okay? And when your delta G naught is negative, for a reversible reaction, you will have predominantly product because the reaction is spontaneous. So it's the same concept. Okay? Alright? Now, I must tell you that when I taught you the equation, delta G naught is equal to minus RT ln K, I have taught you something that is more than the syllabus. Okay? Alright? Because what the syllabus requires you to know is that, okay, we already know that when delta G is less than 0, it's a spontaneous reaction. We already know that when delta G is equal to 0, it is at equilibrium. What the syllabus requires you to know for equilibrium is this: how delta G naught affects K, and vice versa, how K affects delta G naught. So what they want is for you to tell them that when K is larger than 1, or K is very, very high, delta G naught must be negative. All of the reaction will proceed from left to right, and the reaction is essentially complete, and you form a lot of product. Okay? And vice versa. If delta G naught is positive, K must be very, very low. So predominantly, you will have mainly reactants and very little product. Okay? Alright? But what I've taught you is I've taught you an equation that tells you how you can link delta G naught with K. Okay? So delta G naught is equal to minus RT log K. Okay? Next bit, we'll look at your Haber process that you have learned before. Okay? Now for chemical equilibrium in the industry, chemists and chemical engineers will be very interested in how to convert reactant to product as quickly as possible. So that involves reaction kinetics that we have learned. If the reaction is reversible, then we will need to modify the conditions of a reversible reaction such that the reactants react as completely as possible to the product. And to tweak these conditions, we need to use chemical equilibrium, which was what we discussed in our very first lecture in Chem Eqm. So what are the factors that we can play with? Temperature, pressure, concentration, catalyst. Okay? So look at the Haber process that we have learned long time ago. Haber process is a very important process even up to today because it's one of the primary sources for us to manufacture fertilizers. We use nitrogen gas and H2 gas to produce ammonia. Enthalpy change is exothermic. Okay? So if you look at the conditions, the temperature is 450 degrees Celsius, pressure is 250 atmosphere, catalyst is finely divided iron, which is iron that has a very high surface area, and also it is mixed with small amounts of potassium oxide and Al2O3 as promoters. Okay? So these conditions you will need to know for Haber process. Now, very quickly, if you want to increase the yield of ammonia, should the temperature be high or low? If you look at it in terms of equilibrium, because the forward reaction is exothermic, decreasing temperature will shift equilibrium position to the right. So this should increase the yield of ammonia. But 450 degrees Celsius is not a low temperature. Why did we choose such a temperature in the first case? Even though the lower the temperature, it will give rise to a higher yield of ammonia, but a low temperature would also mean that you get a very slow reaction and it will take a very long time to reach equilibrium. Therefore, you take a compromise, a 450 degrees Celsius, where it is a compromise between a reasonable yield and a fairly high rate of reaction. Okay? If you look at pressure, if you want to increase the yield of ammonia, should the pressure be high or low? This one is more straightforward. Increasing pressure will shift the equilibrium position to the right to favor less gaseous molecules, right? According to LCP. So high pressure will increase the yield of ammonia. So the higher the pressure, as you go across the axis here, the higher the yield. Okay? But it is very costly to maintain high pressure. That's why once again we adopt a compromise. We use a pressure of 250 atm, which is optimum pressure for reasonable yield and cost. Because to withstand such a high pressure of 250 atm, you must fortify your vessel walls to be very thick to withstand the pressure. Why do we add catalysts? Because we want to compensate for the slower reaction at lower operating temperature. So if you add a catalyst, it is going to lower the time taken for you to reach equilibrium. Remember, a catalyst doesn't change equilibrium yield. So it only shortens the time. The yield still stays the same. Catalysts don't change the yield. Iron is also a relatively cheap metal as compared to a more expensive alternative like ruthenium. Okay? So if you look at this whole process, where did we get nitrogen and hydrogen from? We get it from air for nitrogen, and we get it from methane for hydrogen. So we have two processes to obtain reactants. Then we have the Haber process. Now what is interesting is the last bit over here. Once you have formed ammonia, remember that it is in equilibrium, right? Because it's a reversible reaction. How do engineers and chemists maximize the yield of ammonia? After we have formed ammonia gas, the gases are cooled while maintaining the high pressure. At this process, ammonia will condense and will be separated out from the gaseous reactants. As a result, the partial pressure of ammonia will drop. This will then continue to favor the forward reaction. So this will increase the yield of ammonia. Right, so by constantly removing away the condensed ammonia, you increase the yield. Just like how the washing machine uses repeated wash, rinse cycle to remove the soap and detergent from the clothes. Okay, so this one over here, you must be able to answer this. Why only ammonia condenses but not N2H2? Because of the intermolecular force of attraction, which is stronger for ammonia. Okay, alright, very last bit, Haber process is by this person called Haber. Alright. Now, not only is he very essential for Haber process, but he was also a main player during World War I. Okay? Alright, because the ammonia that was formed was used to manufacture explosives. He was also the person who was involved in chemical warfare during World War I to use chlorine gas as gases to kill off enemy troops. Okay, so with that, we will end here for today. Remember, chemical energetics is going to come out for your common test. Okay, so go and revise and do your tutorial. Okay, I will see you next time. Thank you.